Hi, everyone, and welcome to our live presentation here on Facebook this evening. I'm Dana Thompson, the director of the Brown Planetarium here at Ball State University, and I'm joined tonight with our Constellation crew. Tonight on screen we have Alec. Hi, Alec. How you doing? And we have Caleb. Hi, Caleb. And we also have Melanie. Hi, Melanie. And we have Nicolette in the chat helping out, answering any of your questions that you have, as well as providing some fun facts throughout the presentation tonight. Tonight we're talking all about a special constellation in the north, and that is King Cepheus. Now, Cepheus we've been talking about the past few weeks because he's related to a lot of other constellations in the sky. But let's find out first how to find him. So I'm going to transfer you all over to Mel to help you.
So talking about these relationships with some other constellations, if you saw our episode on Cassiopeia, if you can find that, you know that it will open towards King Cepheus. But if you didn't see that episode, that's okay. We're going to look almost directly north, and we're going to look almost straight up in the sky. And what we're looking for here is sort of an upside down looking house. And that might sound a little bit funny, but you'll see what we mean. So if we look straight north, we look almost straight overhead, we're going to look for an upside down house. I'll give you a chance to try and find it.
All right, so that N does stand for north here. This is the sky after sunset here in Muncie tonight. And we just put up a line here that is bringing us from the northern horizon up to a special star that's always in the north here. And you know that as Polaris, the North Star. And so King Cepheus does look like an upside down house in the sky right now to the left or to the west of Cassiopeia. And if you watched before, you know that Cassiopeia is kind of a W or an E or a 3 or an M shape in the sky. And it's right over here. If you have trouble finding Cassiopeia, just look for a 3 tonight in the sky after sunset in the northeast. So in between Cassiopeia and the North Star, Polaris, is that upside down house. Has anyone found it yet? All right, let's help them out, Mel.
All right, so if we go ahead and show you what we're looking at here, and we see this sort of upside down house. There we go. Now you kind of know what we're talking about. We sound a little less crazy once you see it. But if we look sort of near the North Star, you'll notice there's the point on the top of the house, or I guess the bottom here, because it's upside down. And you notice it's awfully close to the North Star. And there's a reason for that. So if you saw our episode on Draco, I believe, we had a little bit of information on precession. But a quick review here, our north celestial pole is pointed almost directly towards Polaris here, which is why Polaris is our North Star. But if you saw that episode, you might remember that that won't always be the case. So because of precession, our north celestial pole moves in sort of this circular motion over time.
Yeah, and we're gonna show that in just a few. But first, let's back up just a little bit, Mel, because this house-shaped group of stars is King Cepheus, right? It's not like a house constellation in the sky. So King Cepheus is on a throne, he's got a staff, he's got a crown, but I don't really see that here. In this depiction, the lines connecting the stars that make out this constellation here.
I don't think you're the only one.
Yeah, so we actually have a pretty nice drawing from H.A. Ray from his book, The Stars. And we flipped it up right side up here, and it kind of almost makes it so that you can see a face out of this one with the lines connecting the stars in just the right way. So here's the eye, there's a mouth, and the face. And then on his head, you can kind of imagine that to be a crown of some sort, right? So this is kind of, yeah, like
a weird looking dude.
Yeah.
Yeah.
It's not really, it's one of the harder constellations to find, and then also to see what it's supposed to look like. It's supposed to look like a king. So let's see what the system that we use here at the Brown Planetarium depicts this as in the sky. So it makes that upside down house all of that. Looks more like a king with the proper crown and everything, but I don't really see that when I play connect the dots with those stars. All right, so let's go back to the top of the house here, or the bottom of it, since it's upside down, like Mel said. This star right here, which is by the North Star Polaris. And let's see what we kind of went over a few episodes ago about precession with Mel here.
If you can guess what's going to happen, you can put it in the chat.
So we're going to do a simulation. We're going to speed up time, not by hours or minutes. We're going to speed up time by years and years and years, going from the year 2020 into the future. And here we go. We're going and passing years like they're milliseconds almost. So we're already in year 2500. Look back up here. What's happening? This star right here, which is the top of the house, it's a little bit harder to see now, is getting closer to where the North Star was in the sky, in the north here. So what does that mean, Mel?
So that means in about 2,500 years, Gamma Cephei will be the North Star. Maybe not for any of us to be around and see, but it will be. And this star has kind of a different name called Ire, but most people just usually refer to it as Gamma Cephei. But I think there's something also special about Gamma Cephei here. There's more than just this star here, and I think Alec can tell us a little bit more about that.
Yep. So the star Gamma Cephei actually has an exoplanet, which is a planet like Earth, like Mars, but in another star system. So it was confirmed to be an exoplanet in 2002, but it was suspected to be observed or what have you in 1988. And if that's true, if it was Gamma Cephei AB, which is the name, a more like colloquial term, or actually the formal term is Tadmor. But if it was actually observed back then it would have been one of the first, if not the first, exoplanet discovered. So that's pretty neat. And it orbits around the Gamma Cephei, but there is actually another star around it, but it's a little bit less massive, so it doesn't exactly orbit both of them. It just orbits one of them.
So it's not like the Star Wars world.
Maybe, I don't know.
Yeah,
I think the other one's pretty dim, but I mean, I guess it's going to be pretty bright when you're writing it up.
Maybe it would kind of look more like a planet in the sky, because the planets in our sky, they look like bright stars. I guess it just depends on how far away it is.
Yeah. Unfortunately, we don't know a whole lot about the planet in terms of composition, so we don't know if it's going to be, the second Earth. But it does orbit about twice the distance away as we are to our sun, and as a result, it's years longer. It's about 2.5 times longer than our year. So, yeah.
All right, so that's this bright star next to the North Star Polaris. When I'm finding Cepheus in the sky, I always look for Polaris first, and then I kind of look off in between Cassiopeia. So Cassiopeia is over here. And Polaris. And I find that first, and then I have to figure out what way to go to find the rest of the upside down house, or sometimes it's upright, because it's another circumpolar constellation that we've talked about before, meaning that it doesn't really rise or set in the sky. It just kind of goes around in a circle around the North Star. All right, what do we got next here? This is a beautiful picture. What's going on here, Alec?
So what we're looking at is a Seafied variable star. So you hear variable, so that means it changes. Well, Cepheus variables do actually change. We can only see the fact that it gets brighter and dimmer. It does that because Cepheus variables actually pulsate in terms of how big they are. So they get bigger, and then they get smaller and bigger and smaller, and they keep doing that. So you can kind of see this animation. It's pulsating pretty obviously. And what's really neat about it is that the variation is cyclic, but also that there's a direct relationship between the pulsation period. So you can see on the graph here, the brightest part, which is the peak of the graph, and then it gets smaller, and then that's the lowest peak, and then it gets bigger, etc. But its period, so the length between two of the peaks, is directly related to how luminous the star is, and that's kind of just a fancy way of sort of like a calibrated brightness. So it's going to be a brightness that it doesn't matter how far away you are, and because of that, because we can know the luminosity because it's independent of distance, we can actually use the Cepheid variable stars as distance markers. So we can tell how far away it is, and then therefore we can use for other things. So
yeah, because distance
pretty
is
important.
so hard to find in space. Like we can't take a ruler and measure the distance to objects. So it's quite difficult. So having these variable stars here to really help us get those distance measurements is really important. Do you know why it goes to a smaller size at a shallower slope than it does to the larger one?
You mean why it's not like symmetrical?
Yeah. Like why does the time to get smaller longer than to expand?
I don't know. It might have to do with the fact that it, like shrinking or expanding really quickly is a very stressful event, maybe. I don't know. I'm not sure.
Yeah, it's interesting. We'll have to look that up later.
Mm-hmm.
All right. So what do we got next?
Aren't most star systems binaries? I think there's more in this constellation.
Yeah. Well, here we got next is a unique star known as Mu. It is Mu. I think it's pronounced Mu.
Like the
Mu
Greek letter.
Yeah, the letter Mu. It's a star in the constellation of Cepheus, also known as Herschel's Garnet Star. William Herschel was a pretty famous astronomer in the 18th century. He discovered a lot of things, which included the planet Uranus. So he's a pretty big name in the history of astronomy. This is a red supergiant that's actually pretty actively visible to the naked eye, and one of the largest stars that we can see with the naked eye. This star is about 1,000 times the radius of the sun, and it's big enough that if it was placed in the middle of our solar system, it would reach out to the orbit of Jupiter. So it would engulf all the inner solar system out to Jupiter. So this here is a diagram showing how big the new Cepheus is compared to our sun and our solar system.
Yeah, so the sun is
So-
a little tiny dot there. And then just to expand it, I'm not really sure why they did that in this graphic, but if you want to imagine the sun, you can see it here. But basically that little dot there is the sun. Here's the orbit for planet Mercury, and then Venus here. Earth and our moon's orbit is here, and then Mars here. So just the inner solar system. It doesn't even include Jupiter, Saturn, Uranus, and Neptune here. All right, but there's more.
Yeah, so we have another variable star actually known as VV Cepheus, or we know it's similar to Mu Cephei in that it's a red supergiant, and this one is a variable star as well, which leads us to believe that there is another star, which we have kind of confirmed. So this red supergiant is paired with a blue main sequence star, which they cleverly named VV Cepheus b. So you can kind of get an idea of the naming system here. We know that this is at least 5,000 light years from Earth, but again, distances are hard, even when they're not 5,000 light years. But we know that this red supergiant is one of the largest stars in the galaxy. So similar to Mu Cephei, it has a diameter of 1,400 times that of our sun. So we know that the size of this red star is nearly as large as the orbit of Jupiter, which again is similar to Mu Cephei that we just talked about.
So the
And we
sun,
also,
the sun's
yeah.
that little tiny dot there, and the sun fits in this graphic, but VV Cepheus doesn't fit, and so this is just the edge of the star here. And you can just slightly see the curvature of it up next to the sun.
and the sun always seems so intimidatingly large.
Mm-hmm.
That really puts it in perspective.
Yeah, it's 109 times wider than Earth, and Earth is huge for us, you know, so 109 times wider than Earth. Like, you wouldn't be able to see Earth, I think, on this scale here.
Yeah, it's hard to even think about. But yeah, when this red supergiant gets close enough to the blue star, we actually see matter shedding onto the blue star. So some of this material is leaving this big red star and moving toward the blue star. And as they kind of get further apart in their orbit, so sometimes they're a little bit closer, sometimes they're a little bit further, similar to kind of the moon and the Earth, as well as the Earth and the sun. Really anything that is orbiting has a point where it's closest and a point where it's farthest, on average. But we know that as they get farther apart, this kind of gets cut off, so they're slowly maybe evening out. I'm not really sure how that would end up. I don't know if any of you know, like, the probability of matter shedding from one star to another. Do they always end up equal? Does one kind of eat the other?
They end up in, like, thermal equilibrium. So I think their colors, their temperatures equal out.
Okay.
And then there's different types of supernova events, right? I think that sometimes there's a critical mass for the one that the matter is falling onto, and it can kind of spark some explosions out in space.
That makes sense.
Alec, do you know more?
About what happens to them eventually?
Yeah.
I do not know exactly.
Yeah. Caleb, how about you?
I'm sorry.
All right, we're gonna have to look it up afterwards.
Yeah, you can imagine. I mean, that's what happens to me if I eat too much. I feel like I'm gonna blow up. So that kind of makes sense. I'll go with that option. But there is one more thing that's special about this specific variable that I think Alec can explain a little bit as well.
Yeah, so the Seafied variables that I talked about is actually a type of variable star in addition to being, I believe, in the Cepheus Constellation. But the VV Cepheus A is variable for a different reason. So the other one was the star was actually getting physically bigger and brighter and smaller. But this one actually is an eclipsing binary. So that means that the variation in the brightness comes from just one of the stars going in front of the other. So there's nothing necessarily pulsating or changing about the stars themselves. It's just the orientation from us to them. But because it's so huge, they have to be really far apart, naturally, because otherwise it would get swallowed up. We learned that it's about distance out to Jupiter. And it has one of the longest period of eclipsing binaries, and it's about 20 years. Unfortunately, the variation in brightness we couldn't really see with the naked eye, which is normally the case, but also you couldn't imagine because the other star is so gigantic that, the tiny one just going in front of it or vice versa is not going to make a difference.
Do we actually get transit from our perspective? Like, is it kind of face on like that?
Edge on, you mean?
Yeah.
Well, I would imagine so, because otherwise how do we know that it's eclipsing binary? Right? I don't know.
Yeah, I mean, it would just be a binary, right?
Right, yeah.
Yeah.
I'm assuming you'd have to use some very sensitive equipment to sense it. I'm not sure how sensitive though. Wonder if we could do it with the rooftop at Cooper.
We could sure try.
But
Yeah.
also it's every 20 years, so. Well, I guess every 10 years it eclipses, right? Because you have
Period, yeah.
one of the eclipses and then it goes 180.
But we wouldn't see the other one. Well, I guess, yeah, it would just be a dimmer.
Yeah, we could see both,
yeah.
I would think.
Yeah, it just depends on how sensitive it is. Yeah. All right, so in this area of the sky, this area is called the Cepheus Constellation because it's King Cepheus. All the stars here are part of that constellation, but there's more in this constellation. This whole little puzzle piece here that I'm drawing out. Not exactly, not perfectly, but everything in this region of the sky is in the constellation of Cepheus, like the stars we talked about. But there's more than just stars, right, Caleb?
That's right. We're going to see a very unique object here known as the Bubble Nebula. This is a nebula that was formed when the central star, which if you look here at this animation, is that bright blue object right near the middle of it, expelled a shell of gas and dust. This was about 300,000 years ago. This dust was expelled from the central star, and when it interacted with the nearby molecular cloud, it formed the bubble shape. Now we can see this nebula because light from the central star hits the gas and dust and energizes it, which allows it to give off light. There's a pretty common way how we can see nebula when light from other stars can energize the gas and dust and allow it to emit light.
Yeah, it's beautiful. So this is a real picture of it. The other one that we saw, we were kind of flying through, it was an animation based on real data, or data that was taken, and it's a realistic fly through. But we've never actually sent spacecraft to go and explore these things. This is all just being inferred from telescopes here at Earth. But it's definitely beautiful. What do you think this is? This little squiggly? It's maybe a solar system information.
Looks like a sword.
Yeah, it does.
I don't think it's a sword.
I wanted to pop the bubble.
Oh my gosh. That's good.
Yeah.
I want to know what that is now.
It could be part of the molecular cloud.
Yeah. And these aren't purple stars. Like that's false color. So that's not actually what our eyes would see. Because there's no purple stars unless you want to talk about like brown dwarfs or something, which we're not going to get into.
Yeah.
Darn it.
Not today anyway. Maybe next time. All right.
Search for purple stars.
Yeah. The students, the kids who come for our school group presentations in the planetarium, or when they used to come, they would just get really disappointed that there's no purple or green stars. But
I'm disappointed.
yeah. All right. Mel. All right. So besides stars, besides nebulae, like Caleb mentioned, we have galaxies too. like this beautiful one, which is another false color image. It's not really purple. Sorry, folks.
Yeah, so this galaxy is called NGC 6946, which is kind of a lame name, but there's a cooler one to come. As you can see here, it's kind of a face-on spiral galaxy, so we really get the full view, which is really, really cool to see. It really makes for beautiful pictures here. So all the way across, we're at about 40,000 light years for the entire thing, which might sound like a lot, but it's actually only about a third of the size of the Milky Way. So again, the name isn't that cool, but the name that's kind of popping up and becoming more popular is the Fireworks Galaxy. And that's because there are so many supernovae happening within the galaxy, like significantly higher than what we're seeing in the Milky Way. So on average, in a galaxy the size of the Milky Way, we would have about one supernovae per 50 years, and we're seeing way higher activity here. So again, as Dana said, with the false color on that first picture, it's caused because we're combining X-ray as well as optical light. But the reason they use X-ray is because we can actually see the supernovae a little bit better. But another reason that the amount of supernovae is really exciting is because this galaxy only has about half as many stars as the Milky Way. So it just makes it that much more significant. And again, it gives us really beautiful pictures like we can see here.
Looks like a firework.
It does.
A really expensive grand finale firework.
So,
But also, you have gas that the stars are going through, so I would imagine it wouldn't be impossible to make a purple sort of appearance.
yeah,
Maybe.
Yeah,
There's got to be hope.
like maybe an appearance
aren't
of one, but
those-
not like an actual like intrinsic like light that's shining.
Yeah,
or
right,
being
right, yeah.
formed. But yeah, we can definitely maybe have the appearance of one.
Have there been aurora that were purple or like different colors on elements?
Yeah, purple comes from nitrogen in our atmosphere. Our atmosphere is about 80% nitrogen. And so the aurorae are created by streams of charged particles from the sun, electrons and protons, and they get funneled in through our magnetic field lines where they connect and come from the Earth, so the North Pole and the South Pole. So they get funneled in through there, and they interact with our atmosphere, and it makes it shine. So the nitrogen in our atmosphere shines blues and purples, and the oxygen in our atmosphere is like reds and greens, because our atmosphere is 80% nitrogen and about 20% oxygen.
We're just trying to find a way to make things purple.
Yeah, I mean, it happens. There's a lot of the spectrum tubes that we use for activities sometimes. Those are purple. I think almost every one of them is purple. So there's a lot of elements that, you know, shine in different colors, and nitrogen will shine in purple. And there's neon too, right? That shines bright orange, like neon lights. And if you see like a neon light and it's not orange, it's not actually neon inside. Okay, what do we got next? All right, besides galaxies, besides nebulae and stars, there's black holes. Out in our galaxy and in Cepheus, there's one of the largest known black holes. So you can see a depiction of one. This isn't an actual picture. This big circle here, that's the event horizon of this black hole compared to the size of our solar system, which is this little guy here. It is 40 billion times the mass of our sun and 37 times the size of Pluto's orbit. And I don't know if you know, but black holes actually have a lifetime. They don't live forever. Black holes can die, just like stars do. That created that nebula that we saw before. Or was that a nebula from a star dying, Caleb, or was that a cloud that was formed from a star being born around it?
I think it was I believe it was the star shed like dust and gas.
It was maybe
Um,
dying then, or something.
Yeah.
Something happened to make it shed that. So
Yeah.
stars do die, and they usually form those pretty nebulae that we see, planetary nebulae, for instance, like we've explored before, like the Ring Nebula and so on. But black holes will die too, due to something called Hawking radiation. And we're not going to go really too much into that, but it's saying that this black hole is going to live 10 to the 88 times the universe's current age. And the universe is really old. It's 13.7 billion years old. So much, much longer than the life of our universe. Do you all know how long stars live?
I guess it depends on the size, right?
It does. It depends on the mass of it more than the size. It's the size is a part of it, of course, but the mass, how much material is there. So what about stars like our sun? How long do those live?
Stars like our sun, which are on a medium mass, last for billions of years.
Yep.
Our own sun main sequence lifetime is about 10 billion, roughly.
And we're about halfway through that. So our sun will live for 10 billion years. It's about 4.7 billion years old now. But what about stars that are more massive than our sun?
They have shorter lifespans.
They do.
So hundreds of millions.
They live for millions of years, yeah. So
just millions.
So stars that are larger than or more massive than our sun live for millions of years. Stars like our sun live for billions of years. What about low mass stars like red dwarf stars?
Even longer.
Even longer.
They can last for trillions of years, longer than our universe is even alive. So,
yep. Trillions of years, longer than the age of the universe. So we haven't really seen a red dwarf star at its final stages of its life. So it's interesting to think about. I wonder what the space for where a black hole used to be will look like. I wonder if the space-time will still be curved, or if it would, bounce back. I don't know. It's interesting. All right. Well, I think that's really all we had to talk about with King Cepheus. Mel, do you want to give a quick wrap-up of how to find it again in the sky?
Yeah, so as Dana said, I like her way better than mine. Look for the North Star first, because I think most people can usually find that relatively easily. Just look directly north, go straight up from there, find the North Star. And if you look just up to the right a little bit, did you say it was slightly west?
Well, we're facing north here. So west is on our left.
Okay, so slightly east of north. Or just up and to the right if you're facing the North Star. That's an easier way.
Yeah, I like right and left. I'm not really a big, I learned my directions for astronomy and for the planetarium, but I'm not really big on directions. I like my right and lefts usually.
That's a lot easier.
Yeah.
So yeah, just up and to the right and look for that point star, Gamma Cepheus, and then just kind of build your way to an upside down house from there.
Yeah, so kind of make a triangle maybe and see if you can get these two down here.
If you can find any of it, I will be very proud, because I always have a hard time finding it.
It is a hard one to find. I always struggle, and even to this day, and sometimes it's easier to find different times of the year, even though it is up all year round, because it's a circumpolar constellation like we mentioned. Even though it's up all year round, sometimes it's just a little bit higher in the sky, or it's orientated in the right way that it just pops a little bit more. Okay. All right. Well, I put a link to our first annual Astronomy Slam in the chat. So be sure to check out our Astronomy Slam tomorrow at 6:30. We're going to be live on Facebook again, and Melanie and Alec are going to be presenting along with Ricky, who's a part of the Constellation crew, and another student here at Ball State, Belle. So Belle is going to be joining us for the first time on Facebook Live, and she's going to be presenting about women in astronomy. Mel, what are you presenting on?
I'm presenting on sound in space.
And Alec, what are you presenting on?
Eclipsing binaries.
Eclipsing binaries. So kind of, we talked about those today. So you're going to hear more about how those work. And what's Ricky presenting on? Anyone?
The end of the universe.
The end of all things. So Ricky's going to be talking about the end of all things.
The end is near. The end is near.
Really cool. It's the last one. And we're going to have a winner, an Astronomy Slam champion. There's a really nice award for it. And then there's other awards for most engaging or energetic presenter and best visuals. And what's the last one? Most thought-provoking as well. So we really need you all to watch that event and vote. Vote, so that we can get those winners and really, really congratulate our students here at Ball State. All right, final thoughts, crew? Okay, there is one question, and I think Nicolette answered it, but the question is from Christopher Harrison. Great guy. Do certain star types occur more frequently towards galaxy centers versus the edge? I wonder if we can go back to your galaxy here, Mel.
Yeah, doesn't that also kind of depend on the type of galaxy or the shape?
Yeah, so star formation, like in these spiral, we have density waves. So there's waves of more dense material here. So there's some gas clumping, and there's this traffic jam when things are going around the galaxy. And so those traffic jams slow down material and condense it and really spark star formation. So I wonder how that is affected out when you see these long spirals versus in the center region where things are really dense in general. Any thoughts on that, Alec or Caleb? So the question is, do certain star types occur more frequently towards galaxy centers versus the edge? Nicolette said... Go ahead.
As I understand it, within spiral galaxies, especially within dust lanes, star formation tends to happen a lot more in the dust lanes. So, like these dark areas right here, usually that's where newer stars are born. So, from what I understand from my classes, a younger star is going to be in the disk of spiral galaxies. So.
Yeah, so I mean, there's different like populations of stars. There's different ages, but I wonder. I'm not sure about the type, how it affects the type. Chris, we'll have to get back to you on that one. Yeah.
I would imagine that the center is probably a little different, just because it's kind of just probably a mess in there.
Yeah.
Because it could probably get pretty dense and hairy, but I'm not sure.
Yeah, and like how's the matter distributed, right? So there's more matter here in the middle than out towards the edges. So if there's more material, would you form larger stars than towards the outer regions? I don't know, because like we're about 2/3 of the way out from our galaxy center, and we observe stars of all different sizes in our sky, in our region that we can explore. So it's a pretty good mix. I'm gonna say it's pretty mixed, but I'll have to look it up.
We should also take note that most of the mass of our own galaxy is mass that we can't even see, which is a whole other topic entirely. So.
Yeah, well, we're going to save that one for another day. All right. Let's wrap it up here with this beautiful picture of, what is this called again, Mel? Because it's got a really not... It's the Firework Galaxy. That's what
Yeah, let's go with that.
It's the Firework Galaxy. It has another name, but all you need to know, this is the Fireworks Galaxy.
Yep.
Wonderful. All right. Thanks for tuning in, everyone. Check us out next Friday. We only have 2 more Constellation Crew programs. Next week, we're going to be talking about Pisces and Mars because Mars is in the constellation of Pisces, the fishes. And then the week after that, we're going to be talking about all the cool things we explored this whole semester before our students go online for the rest of the semester and then have their holiday break. So check us out for those. But tomorrow, 6:30, we have Astronomy Slam. It's going to be amazing. So please come and check us out there and vote for your favorite presentation during that. Thanks so much for watching, everyone. Have a great evening, and we'll see you tomorrow.